like this. And then this is the density of a conserved quantity. So if you integrate this quantity over a fixed time slice of your space-time, then you will find some number, and that should be independent of time. Okay, so that will give you some conserved number. Now, if this is the case, then the spatial components of J are telling you how the conserved quantity is being, now being followed.
Yeah.
Okay. Okay, so then the spatial components of this vector will tell you something about transport. So you have this conserved quantity, and Ji will tell you precisely how this conserved quantity is moving around space-time. So the current Ji, the spatial components, describes transport of the conserved quantity. Okay, so for the electric current, that you find from a derivative of the partition function with respect to the external gauge field, there is a clear current you can define. However, for the stress tensor, we found something slightly different. It was not quite a vector. All right, so the word identity we wrote had the field strength of the external vector field. We had derivatives of the scalar sources. It was something like this. Okay, so now I want to construct a conserved current from this. It's not yet a conserved current. It is an object with two indices. And I want to write something that satisfies this equation, a vector, basically. So how can I get a vector from a tensor? Well, I can get a vector from a tensor by contracting with a vector, okay? So let's try and do that. Okay, now I want to say that for any vector, just pick your favorite vector, whatever that is, and let's call it k nu. We can write the following relation. So if I take the divergence of T mu nu plus J nu A nu, and I contract this with the vector, right? So I have contracted T mu nu is the stress tensor, J mu is the expectation value of the current, A nu is the external field source, right? So that's not dynamical. So then by using the word identity, I can write the right-hand side, which is equal to T mu nu, the VEV, contracted with the Lie derivative of the background metric plus the expectation value of the current contracted with the Lie derivative of the external gauge field, the external vector source, plus the Lie derivative along K of the external source phi s times the VEV of the scalar. Okay, so now let me pick a particular vector, right? So I have some vector here which is almost divergenceless if the right-hand side is 0. Okay, so remember that these guys, J mu nu A And phi s are backgrounds. They're stuff that are fixed by me. Okay? So then I can make the following statement. So if the background, this is the background, G mu nu, A mu, and phi s. So if the background sources are invariant under the following change of coordinates, x mu goes to x mu plus k mu infinitesimally. There is an epsilon here, so if I make this small change of coordinates and at leading order in epsilon, my sources are invariant, then the Lie derivatives of the sources with respect to k will be 0. Okay, so then the Lie derivative with respect to k of the metric is going to be 0. The Lie derivative of the external gauge field will be 0, and the Lie derivative of the scalar source will be 0. So as long as k is generating some isometry, of the backgrounds, then this quantity that I can construct from contracting T mu nu plus J mu A nu with K nu will be a conserved current. Okay? So if these conditions are true, then the vector, let me call the vector J, which is, whose definition is based on the vector K. Then this is conserved. Okay? So as long as I have some symmetries in the background, the metric has some symmetries, the gauge field has some symmetries, and the source has some symmetries, I can define conserved quantities. So one of the conserved quantities that we are super interested in is for the time-like if the generator of time translations is also symmetry of the background, meaning just a static background, then I can define a conserved current. Let me call it Q mu, which is the J that I can construct from partial T. And this is called the heat current. Okay, so why do I want to call this the heat current? So let me first of all write down things in terms of the vector. So if k is just partial t, there is only the kt component, which is non-zero. It's just 1. All the other components are 0. And so this current is simply minus t mu t plus j mu at. Okay? So then the conserved quantity would be the jt component, the time component. Okay, so let's write it here. Then jqt would be minus t t t minus jt at. Now, TTT is basically the energy density of the system. AT is the chemical potential. Okay? And JT is the charge density of the system. So basically, I wanted to study transport of this quantity. But why do I want to call it a heat current? Well, Let me think of this quantity in terms of just thermodynamics, okay? There is no funny dynamics happening. So, and let me take a variation of this quantity just for a thermodynamic background. With respect, so let's go to the grand canonical ensemble. So the fixed quantities that I will have are temperature and the chemical potential, okay? So if I vary this quantity with respect to temperature and chemical potential, then I will have delta E minus mu delta rho minus rho delta mu. I can use the first law of thermodynamics to write the variation of energy. And that will give me T delta S, where S is the entropy density, plus nu delta rho minus nu delta rho minus rho delta mu. So these two guys are going to cancel out. And so a variation of the time component will give me this. Okay? So the time component of this vector, or this vector at fixed so this vector is really describing transport of heat, which is T delta S, at fixed chemical potential. So from the holographic point of view, I mean that the quantity that I should be interested in is really the spatial components of this vector, correlation functions of the spatial components of this operator. Yes?
The fact that you take AT equals to mu, right?
Mm-hmm.
Could you think that there is a gauge choice there? I understand that mu doesn't vanish at infinity, so it's a bit of a, like a large transformation. But could I have chosen AT equals 0?
And
like
still
this?
have charge?
Tell me again.
And still have charge in the system?
Exactly, yeah.
Well, by doing gauge transformations in the bulk, for example.
Well, this is purely in the field theory,
Okay,
right?
yeah.
Right, so I can make a gauge transformation in AT and erase the mu if I allow myself a gauge transformation that doesn't vanish at infinity.
But then I think TTT would change.
Because the definition, because of that?
Yes.
Okay.
Well, even if I think of the partition function, I think I'm not
only, which is gauge invariant, right?
right. That gauge transformation, I mean, on the thermal circle, that could be non-periodic, right?
Because it's a large gauge transformation.
Yes, exactly.
So it's a bit tricky.
Yes. Yeah. I mean, from the holographic point of view, you would see it as some singularity on the horizon. If you tried to take Euclidean time, you would find that the bulk gauge field could be singular at the horizon. Yes.
That creates time dependence in other places, and that most likely will also tell you that the scaling
Is problematic. Yeah, so if you do, I mean, again, from the holographic point of view, if you make this gauge transformation, you have to also do stuff with a radial coordinate in the bulk so that everything is regular on the horizon. But then you cannot have the Euclidean version. I mean, from the relativistic point of view, that's absolutely fine. But when you try to compactify time, it would be problematic. Okay, so yes, if I have a time-like Killing vector, partial t, I can define heat if I have a space-like killing vector. That could be basically momentum. Then what we would call the momentum density would be the current that you can construct from parcel I. Okay, so, right. So what we are interested in is two-point functions of the ji's and the jq's. And this is related to the transport coefficients that I wrote in this nice conductivity matrix before. So
Aristos,
yes.
there was a question on the chat. If the electromagnetic vector potential mu describes a background electric field, does Q obey a covariant form of Ohm's law?
Does Q? I think that's called the Fourier law. There is a name for, yeah. What's really the question? Can you? Well, the background A mu is not really an electric field, right? If the field strength of A mu, which is the background, is 0, then there is no electric field.
Maybe it should be like the thing you explained before, where you had the matrix and you said the first component is Ohm's law.
Yes.
Maybe another way this could be asked is the Q component, does it obey the linear law?
Oh, that JQ is, yes. This is reflected in what I will, I think, write it down. So sigma would be the retarded Green's function divided by I omega. That could be, I think, Ohm's law. And indeed, Fourier's law, I think it's called Fourier's law, is that the thermal conductivity would be the two-point function of the heat current. Does that answer the question? Okay, good. Thanks. Okay. So this is what we are interested, I mean, these Green's functions is what we are interested in extracting from holography. Okay. So now, after having sort of set up the problem from the field theory point of view, now we can talk about the Z=1 backgrounds, which is really ADS, the geometric realization of these backgrounds. So the geometric realization of the conformal group. Okay, so what have we said? So we said that the conformal group in d dimensions is equivalent to the Lorentz group in 2 plus d dimensions. So a natural thing to consider is R, 2 comma d, with the Minkowski, not the Minkowski metric, with the metric with a couple of minus signs in the metric. I can use something like Cartesian coordinates. Where I and j are running from between 1 and d. Now, this metric, it could be the geometric realization, except for the fact, well, that indeed the symmetry group is SO2, D, but you also have translations. So if I do translations in either U, V, or the xi's, these are isometries of this metric. So this metric has more symmetries than what I am after. Okay? So what could break the translational symmetry is just the surface. Okay, so the surface u squared plus v squared minus delta ij xi xj equals to some number L squared, it certainly preserves SO2, D, but it breaks translations. Okay, so that's exactly the surface that realizes the symmetry that I'm interested in. Okay, it's like taking a sphere in R3. I mean, R3, what are the symmetries? The symmetries are SO3 plus translations. If I just take a sphere at the origin, I will keep the rotations that I'm interested in, SO3, but I'm breaking translations, right? So that keeps precisely the symmetries I would like to have. Okay, so I want to write some nice metric on this surface. So you can just solve the constraint by defining appropriate coordinates. So you can take, for example, u to be 1 over 2r, 1 plus r squared, then L squared plus xa minus t squared. You can take v to be L RT, and xa is L R xa, and then xd. Well, whenever you see a here, it runs from 1 up to d minus 1. And then xd will be 1 over 2r, 1 minus r squared, L squared minus xa plus t squared. And then if you find the induced metric on the space, which is parameterized by the d minus 1 coordinates xa, t, and also the coordinate r, then the induced metric is ADS in the Poincare coordinates. You will have L squared, R squared, times minus dt squared plus delta AB dxa dxb plus L squared dr squared over R squared. Okay, right. And what you discover here is a D+1 dimensional space, which is guaranteed by construction to have the conformal group as its isometry group. Okay, so what I want to focus more on is that the Poincaré symmetry of the conformal group, the Poincaré subgroup, it's fairly obvious in this metric. So if I write this as L squared, R squared, eta mu nu, dx mu, dx nu, plus L squared, dr squared over R squared. So the Poincaré symmetry is just obvious from this form. I would just have to take XA and contract it with a Lorentz boost. But what is slightly more interesting is the scaling symmetry. So the scaling symmetry is simply scaling the XA coordinates by some number lambda, and the R coordinate in the opposite way. Okay, you see that the role of this R squared here is precisely to cancel out this lambda squared you will get from the X's. You have the R squared over R squared, so that will be invariant under scaling symmetry. Okay, now from this way that things transform, you can probably tell, roughly speaking, that the R goes to infinity part of the geometry correspond to small distances, right? So if I want to go to, I don't know, large R, it's equivalent to taking lambda small, but taking lambda small is like taking small XA. So that could correspond to small distances. So the R goes to infinity part of the geometry is the UV part of the theory, corresponds to the UV. And in the opposite way, the R goes to 0 limit is the infrared. Okay. Now what? Yes.
The argument by the UV part of the theory are tending to infinity.
So if I mean, going to large R is like going to small, multiplying by small lambda, right?
Okay.
Okay, and multiplying by small lambda means I'm taking small distances from the boundary point of view.
I see. Okay. 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 Yeah.
Okay. Good. So what do I want to say about this geometry? I mean, just writing this down is like having written down the vacuum of the CFT, right? The vacuum should be invariant under the conformal group. This geometry is invariant under the conformal group. So you could say that this geometry corresponds to the vacuum of the CFT. So the equation that this geometry solves, the gravitational equation that this solves, is Einstein's equations with a negative cosmological constant. Right, so if you compute the Ricci tensor, you will find that it is proportional to the metric. And in fact, the constant of proportionality is minus d minus 1 divided by L squared, where L squared is like the radius of ADS times g mu nu. Okay, so that's a minimal theory. Einstein's theory with a negative cosmological constant is a minimal reasonable theory which has ADS as a solution. Okay? However, ADS is not the only solution that Einstein's equations have. Einstein's equations with a negative cosmological constant have. They have more solutions. And they have more general solutions which only asymptote to ADS in the R goes to infinity limit. I will say more about this when I tell you about the theories, the gravitational theories that I will be interested in. Right. So we have found a minimal gravitational theory which can accommodate the vacuum of a CFT, and which is reasonable to consider as the low energy limit of some quantum theory of gravity. But let me tell you what kind of holographic theories we are going to be interested in the context of ADS-CMT. So what I'm mostly interested in from the condensed matter theory point of view? Well, I hope I convinced you that an interesting object to consider is the stress tensor for many reasons. I also want to study conserved currents, conserved electric currents. And I also want to consider in my theory scalar operators. Why do I want to have scalar operators? Well, because just the CFT, an undeformed CFT from a condensed matter point of view is, it's probably not the most interesting thing you can consider unless your condensed matter theory system is described by a CFT itself. So as I told you, I want to take conformal field theories, deform them by relevant operators plus chemical potential, and flow to interesting fixed points. So to do that, we are definitely going to need scalar operators which are relevant with respect to our UV theory. From the bulk point of view, of course, I will definitely need the metric, because as I will describe in a while, the sources for the metric tensor from the gravitational point of view are basically the asymptotics of the bulk metric. For the same reason, the sources for the conserved current are going to be given by the asymptotics of Maxwell fields in the bulk. And scalar operators from the boundary point of view are going to be sourced by the asymptotics of scalars in the bulk and their asymptotic expansion. Okay, so this is the field content of the theories in the bulk that will be of our interest. Right. Now, someone can say, okay, just take some theory, write it down. You have found some Lagrangian, do something. Well, I would really like these theories to actually come from dimensional reduction or from a theory of quantum gravity, right? And very good examples of such classical limits come from higher dimensional supergravities, like 10-dimensional supergravities or 11-dimensional supergravity. Now, so these lower dimensional theories, I want to imagine that they come from a consistent trication or from a dimensional reduction of these higher dimensional theories, right? Which are nice. They do come from from the low energy limit of some quantum theory of gravity. And I can think of these dynamics as being part of the the dynamics of the bulk theory as being really dynamics of these higher dimensional theories. And that brings me to saying a few things about consistent Kaluza-Klein truncations. So let's say that we are either in a 10-dimensional or an 11-dimensional theory. Now, yes? No, not at all. Should it be some theory of gravity? Okay. Right. So yes, you can write anything you like, but you cannot trust it. Right? So what I want to say is that, okay, I'm taking this theory. I want to do some deformation. It will flow to some IR. Okay, some IR theory, some fixed point. Now, if your theory is just cooked up, you wrote anything you like, you will get any IR fixed point you like. We know this cannot happen. There is very fixed IR fixed points. They are very discrete. You cannot have 3 parameters. This dynamical exponent cannot be anything. They are quite isolated fixed points. Now, so yes.
So we want the bulk theories to be truncations of supergravity theories, not the CFT, right? And that
no, I want the bulk theory to be truncations of supergravities.
The condensed matter systems will be described by the CFT. So I think
well, okay. I will get something that I hope that I can trust in this way in the low energy limit, right? Well, physical motivation is that I cannot get any low energy limit I like. So the equivalence from the gravity point of view would be, let's write any classical gravity. We know that it cannot be that any classical gravity can be the low energy limit of a quantum theory of gravity. Well, I mean, there is, for example, general theorems which prevent certain features from quantum theories of gravity. I can still insist that there is some global symmetry, for example, in the bulk of a classical theory of gravity, but you know that from the quantum gravity point of view, you cannot have a global symmetry. So there is that. So if I want to trust something, it really has to have some microscopic description, and in order to have a microscopic description, it has to come, well, it's good to come from a string theory where I know what I'm doing. But even then, if you find the low energy limit of whatever the good theory of gravity is, you are doing something which again might not have which you might not be allowed to do. So first you have taken a large N limit in order to have a classical theory of gravity, and then you take the low temperature limit. You can do that, but if you want to say that I have a condensed matter system and I would like to have the opposite, first take the low temperature limit and trust what I'm doing in the large N limit, it's not clear that these two things commute. That's the second stage. But at the first stage, if you really want to take the low energy limit, even in the large N limit, it better be from some theory of quantum gravity. Okay? Yeah. It is a necessary condition. If there is other nice. Yeah. Which theory? Yeah, but is it for the boundary theory or the? Okay. It is a way. Right. Yeah.
Another way is that doing it the way you suggest, I think, you guarantee that you will have a consistent way of improving your calculation.
Exactly.
Right.
It could be more under control.
Whereas in any theory of gravity, you will not, because you don't know the theory how it's corrected, right? So
Yes.
this is one way of thinking.
Yeah. Yeah, for these specific theories, things are more under control. There might be other theories, which I don't know about, and things could be, again, under some control, but...
So
yeah.
maybe
Yes.
another comment is that all our holographic examples are some truncations from string theory. So means we would trust holography more if the bulk theory came from some truncation of supergravity. That's one motivation why we want. Otherwise, we don't know if we can actually trust holography.
I think this is, yes, a rephrasing of what Carlos was saying, yes. The question was about supersymmetry and whether we are breaking supersymmetry. Well, yes. For example, finite temperature will break supersymmetry. That's even just from the get-go. But if you say, okay, what about the zero temperature limit? Can we have supersymmetry? In that case, yeah, why not? I mean, there is zero temperature limit black holes, which are supersymmetric. Well, I will have supergravities. I mean, yes, so I will take supergravities, right? And sometimes because of my deformations or because of finite temperature, none of the supersymmetries of those supergravities will be preserved by these backgrounds. If I'm lucky, yeah, some of them will. And there is interesting examples from the condensed matter theory point of view, which are supersymmetric. More questions? Yeah. Okay, so, right. So this bulk theory lives in d+1 dimensions, and I want to take my 10-dimensional space and split it into a factor of this space, which is d+1 dimensional, and then a compact space which is either 10 minus d plus 1 dimensions or 11 minus d plus 1 dimensions. Okay? So let's say that this space that I'm really interested in is parameterized by some coordinates x, and the compact space is parameterized by some coordinates y. Then I will basically decompose all my fields in the 10 or 11 dimensional theory as functions of x and y, and I will simply expand all the fields in harmonic functions in the compact space. Okay, so harmonic functions are complete sets of functions, so I can in principle expand any 10 or 11 dimensional function in terms of these harmonic functions, right? So this is the harmonic expansion. Okay, so this decomposition would basically give me an infinite number of lower dimensional fields, right? So for each harmonic mode, I would be getting a lower dimensional field. That's an infinite set of fields. So what you can do is that you can write down the lower dimensional theory. For the infinite tower of modes. Sin u. But sometimes, and this takes a lot of work to show, is that you can only keep the first few psi n's. And you understand that this is quite non-trivial, because you would still have to satisfy all the equations of motion while satisfying all equations of motion. Right, so, and this is what you would call a consistent truncation. So do I want to write down an example? Yeah, there is a nice example which gives you a pretty simple theory. So let's do 11-dimensional supergravity. I just want to write down the example. I mean, we are not going into much detail. So in 11 dimensions, the bosonic field content is the 11-dimensional metric, of course, and supersymmetry also demands that there is a 3-form, antisymmetric, rank 3 antisymmetric field present. And the gauge invariant object is a 4-form, which is basically the field strength of the 3-form. You can also write it in terms of partial derivatives. Okay, so you take the partial derivative with respect to the A coordinate, you anti-symmetrize everything, you will get the field strength, which is a gauge invariant object. So this is basically telling you that G will be a closed form. And then Einstein's equations in 11 dimensions will be sourced by this 4-form, by the field strength. You will have G A, C1, C2, C3, CB, C1, C2, C3, minus 1/2, DAB, C squared equals 0. And the equation of motion for the 4 form you will have the 11-dimensional antisymmetric tensor, fully antisymmetric tensor, and then a nasty contraction, K1 up to K4, then K5 up to K8. Okay, so these are the equations of motion of the 11-dimensional metric and the 4-form field. Now, you can write down an ansatz for the 11-dimensional field which looks like this. So you take the 11-dimensional metric, you factor out a 1/4, which doesn't play a big role, and then here is your 4-dimensional space. Okay, so this 4-dimensional space is basically this. It will be the bulk of your lower dimensional theory. Now you split out another coordinate psi, which is cyclic. This psi is part of the compact manifold. Plus sigma alpha, you split out a 1 form, and then dy alpha. The y alphas are basically the capital Y's, the coordinates of the internal space. Plus 1/4 a mu dx mu. Now, a mu is a 1 form living in this 4-dimensional space. That's squared plus a 6-dimensional metric which for technical reasons you ask to be Keller-Einstein. Okay, I don't want to say I don't want to say too many details about this. And then there is an ansatz that you can write for the 4 form, which is just 3/8 times the volume form of this 4-dimensional space, minus 1/4 times a 2 form on this 2-dimensional space, and then the Hodge dual of F, where F is just this field strength. Okay, so what are the comments? So the 6D metric G alpha beta is Keller-Einstein. Don't worry if you don't know what this is. It doesn't matter for what I want to tell you. The 1 form sigma alpha lives in this 6-dimensional space. And the 4-dimensional metric is just something general. So if you plug this ansatz in these equations of motion, you will find that everything is a solution of the 11-dimensional equations, provided that the 4-dimensional fields solve the equations of motion that come from the following action. So if your 4-dimensional fields solve these equations, the equations of motion that come from this, then And if you plug in the solution for the 4-dimensional space in that thing, then that is a solution of the 11-dimensional space. So you will have the Einstein-Hilbert term in 4 dimensions. You will have a negative cosmological constant and just a kinetic term for the Maxwell field. Okay, so all these quite non-trivial answers just boils down to something really nice, okay? So this is Einstein-Maxwell with negative cosmological constant. So indeed, I can just set the gauge field equal to 0. I have a negative cosmological constant. I will have ADS4 as a solution in this case. Okay? What is the? Okay, so, right. This psi, together with this Einstein-Keller space, they form together what is called the Sasaki-Einstein space. If this 6-dimensional space is a 4-dimensional complex projective space, then the 6-dimensional complex projective space, then the 7-dimensional space is just S7. Okay, it's just a 7-dimensional sphere. Now, this. So this would be basically M2 branes just sitting at the origin of R8. Okay, and then the gauge field would do something more. It could be a fibration of this 7-dimensional the 7-dimensional sphere over the 4-dimensional space. The gauge field. It's M2. Yes. Yeah. Yeah. Yes. Mm-hmm. That's right, yes. That's because I mean, yeah. Okay, so the question was, is whether you are only allowed to do that on a torus, right, or on a more general manifold like this. If you only have gravity, then I think, yes, you can only do it probably on a torus. But here you also have the 4-form, right? And you can have some curvature on the manifold on which you are compactified. Yes, it's still, exactly, yes. You can do that in this example. In general, no, you cannot do it, but there is, I mean, the examples in which you can play this game are very few. Okay, well, very few. They are countable. There is no general rule, so it is a case-by-case. It is done on a case-by-case basis. In this case, yes, you can do it. And I mean, just for satisfying these equations of motion, it only has to be an Einstein space. The Keller part is because of supersymmetry. So if you want your lower dimensional theory to be supersymmetric, then it has to be Keller. Otherwise, you know, an Einstein space would be equally good, just for satisfying the equations. Yes? Okay, so, oh, okay, yeah. So J is what is called the Kähler form of this space, and the field strength of sigma is precisely J. Okay, yes, sigma does live in here, and it is a very geometric object. Say that again? A mu, why do I have a mu? Because I can keep it. I can just, I mean, from these equations of motion, you can see that I can just set it equal to 0, but it is a field that I can just add and make my theory slightly more interesting. In fact, there is even more fields that I can add to this ansatz, but that would be much more horrible. Okay, so I can have a much bigger truncation than just Einstein-Maxwell. Any more questions? No. Okay, so, right. So this is just a simple example of a consistent truncation, but if I just want to write down what I want to extract from these supergravities, I mean, they will all give me a sector right? So they will all give me a sector which has a metric, right? So we'll have some Einstein-Hilbert term. I will have some scalar field in the bulk, a potential for the scalar field, and a kinetic term, let me call this Z, a kinetic term for the Maxwell field. So in some sense, yes, I can do things quite generally for whatever function V and Z, but getting a dimensional reduction from a higher dimensional theory fixes specific forms for this V and for this Z. So I am going to draw some conclusions from these V's and the Z's, but they'd better come, I mean, they'd better have the form of one of these, coming from these, one of these consistent truncations. So the theories I'm going to be interested will look like this. And you can vary with respect to the metric, the gauge field, and the scalar, and you can write down the equations of motion, right? So if you write down Einstein's equations of motion, you will have the contracted version. Zero. You can write down the equation of motion for the scalar field. This is derivative with respect to phi. And you can also write down the equation of motion for the gauge field. Okay? Now, let me call this equation 1, 2, and 3. So from this general theory, I want to see where is ADS. Right, so ADS was just solving, I mean, we found ADS as a solution of a simple gravitational theory, Einstein's theory with a negative cosmological constant. So where is ADS in this monster? Right. So to find ADS, we need two things to be happening. So the gauge field should be 0, and the scalar field should be a constant. Okay? Basically, well, you can very easily guess that. My matter fields would have to be invariant under the conformal group, and the only vector and the only scalar that would be invariant under the conformal group would be just trivial things like this, okay? So setting the gauge field equal to 0 trivially satisfies equation 3. Okay, so the field strength of 0 is 0. So 3 is automatically satisfied. Now, setting phi equals a constant after having set equals 0 in equation 2. So from equation 2, you get that the derivative of the potential with respect to the scalar field, if you set it at the constant phi naught, should be equal to 0. So this is telling you that V needs to have an extremum, at least one extremum. Okay? Now, if I move on to equation 1, so if it does have an extremum, then equation 1 will give me that R mu nu would be equal to the value of the potential at this extremum divided by d minus 1 times g mu nu. Okay? So then my theory, in order to have at least one ADS vacuum, then the value of this extremum should be negative, right? So because I wanted to solve Einstein's equations with a negative cosmological constant. So V of phi naught would play the role of this cosmological constant. So then if V of phi naught is a negative number, then I can set V of phi naught over d minus 1 is equal to minus d over L squared. And then the radius of ADS that I will have as a solution will be d minus 1 divided by V of phi naught. Okay, and then if V of phi naught is negative, then ds squared is L squared times R squared eta AB dxAB plus the R squared over R squared. Then this is a solution with the radius of ADS set by the value of the potential at the extremum. Okay? Any questions? Yes? In this? Nowhere. Nowhere. I'm just doing things collectively here, right? So any theory of supergravity will look like that. Why should I look at a particular potential or a particular set? Any more questions? No. Okay. The cosmological constant term. In addition? Well, I mean, the theory is a given, right? The cosmological constant term is part of this guy. This is what I wanted to stress in all this maneuvering. Indeed, the value of the potential at the extremum will be the cosmological constant. Okay. Okay, more questions, please? Okay, so ADS is a solution of this thing. What other kinds of solutions can we write down? So let's see. So the other solutions that I am going to be interested in only asymptote locally to ADS. So they only asymptote to ADS. According to the following expansion. So if I think of this metric, of this space, and I think of large, I mean, the regions where the holographic radial coordinate is becoming large, then I want to tell you that there is also solutions which take this form. So the metric takes the form L squared R squared. Okay, this is up to here. But then I can take the Minkowski metric and change it to something else. In fact, if you start expanding the equations of motion, the equations of motion that I have written there, according to the following expansion, to the following R expansion in R, you will find the following. So let me write the first few terms in this expansion, at least symbolically. Okay. Now, to write this expansion, I have fixed a specific coordinate system, which is called the Pfefferman-Graham coordinate system. And as you can tell, the GAR component and the GAR component is 0, and GRR is just 1 over R squared. I can just choose a coordinate system which satisfies these conditions. Now, I want to circle this quantity and that quantity. Now, if you plug in an expansion like this and expand in R, you will find that this function and that function of x, where x is the boundary coordinates, are not specified by the equations of motion. So these are like constants of integration. Okay? So, in fact, this gamma AB is the background metric for the CFT on the CFT side. And this part is another constant of integration, which again you don't fix just by expanding things. In fact, this will be related to the response of the system. And I will write down more precise formulae in a while. Now, for the gauge field, okay. Okay, thanks. This is as far as the metric goes. Oh, and by the way, every other term in this expansion is fixed in terms of these two constants of integration, right? So you can just solve for them term by term. Yes? Right. So this. This is not part of this expansion, right? It is a new constant of integration. Okay, yes, this expansion does follow from the equations of motion, but this is a completely different power. Okay, so D doesn't follow this pattern, basically. So all the other terms in this 1 over R expansion are basically fixed in terms of gamma and HAB-D. Okay, just by solving the equations of motion. Yes? You mean here? Over here? Yes, there is. Yes, this expansion continues. Absolutely. Yes, yes. That was misleading. Thanks. Yes, there is more stuff. I just want to highlight the constants of integration here. Now, if I look at the gauge field, in a large R expansion, then I can write one form which lives on the boundary. Let me call this B. And again, there will be some term that will be fixed in terms of this leading term, plus another term which comes with a very fixed power of R, plus dot, dot, dot. And so here I had made the coordinate choice where GAR is 0 and GRR is 1 over R squared. Here I'm making a gauge choice which has 0 radial component, right? So AR is basically 0. Now, once again, this term in the expansion and this term in the expansion coming with the power 1 over R to the D minus 1 are constants of integration, okay? And in fact, this constant corresponds to the source for the current operator JA. Again, just by looking at equations of motion, this doesn't fix this constant of integration. I will tell you what fixes it. Now, for the scalar field, if I do a near boundary expansion, I will have 1 over R to the D minus delta times any function I like of the boundary coordinates. And again, I'm highlighting the constants of integration here, which will be functions of the boundary coordinates. And phi s will be the source for the dual scalar operator O phi. Now, this delta is the dimension of the dual scalar operator, and it satisfies delta times delta minus D minus 1 is equal to m squared L squared, where this mass is basically the mass that you could get for the scalar field if you expand it around the extremum of the potential, where what I'm calling m squared is basically the second derivative of the potential at the extremum. Okay, so as I told you, I would like this phi to represent a relevant operator. So let me write a little list here. So when m squared, which is again the second derivative of v at phi naught, is a positive number, then the dual operator is irrelevant. Okay, so I cannot just use it to deform the theory. That would completely destroy the UV fixed point. If m squared is exactly 0, then O phi is marginal. And whether you change the IR of your theory or not, it has to be decided at a nonlinear level, so that's a special case. Now, when m squared is negative, then O phi is relevant as long as delta doesn't violate the unitarity bound. Okay? As long as delta is greater than d minus 2 over 2. Or in other words, m squared L squared is greater than minus d squared over 4. So if delta is smaller than d minus 2 over 2, right, this means that the vacuum you have found is unstable, is dynamically unstable. Okay, it cannot be a good ground state for your system. Any questions? Yes. Is the question whether all these statements are a function of the coordinate system that I have chosen? Right. You can do the holographic dictionary without resorting to this coordinate system. Right. You can have an invariant way of extracting the stress tensor and everything. I just want to do stuff with you, so I'm just picking a particular coordinate system just to show you where the interesting things show up as constants of integration. But yeah, if I do a funny coordinate change there in what I have already, then the stress tensor or anything that I will read off will be, the combinations of different things. But yeah, in this coordinate system and with this gauge choice, it is as simple as that. Any more questions? No. So what is the plan in ADS-CMT with all these asymptotics? What do I want to do with this? Okay, so I never told you how these other constants of integration are fixed, right? So I told you that these are sources. You just choose them to be whatever you like. Okay. So let's set up a plan in ADS-CMT. Okay. So the first thing that you can do with these sources is that you can introduce non-perturbative sources, static sources. Okay. And that will trigger an RG flow. Of your theory. Now, once you have that, you can then introduce perturbative sources on top of that. Which depend on space and time from the boundary point of view. On the boundary space-time. To compute the response, to examine the response of the system or the Green's functions. Okay, so this is what you want to do. So you can deform by static sources, you trigger some RG flow in the geometry, and then as soon as you have that, you want to introduce perturbative sources on top of that, and that will let you examine how the system responds with respect to these perturbative sources. Okay, good. So then the resulting geometry, after you deform with these static sources, is going to look something like this. Okay, so this big square is like the boundary of ADS that I have deformed with these sources. Okay, so on this boundary, I have fixed the sources gamma AB, the source for the gauge field, or for the current, and the source for the scalar. But somewhere in the bulk, I want to impose basically that everything is irregular. Okay, and I want to impose that I have infalling boundary conditions. So imposing that in the case that you have a horizon like in these black brains that Jan was discussing before, I mean, I can have event horizons even after having introduced all these sources on the boundaries. I can still have an event horizon in the bulk. So what you want to impose on this event horizon is ingoing boundary conditions. Why? Well, that is a recipe that will let you compute the retarded Green's functions of the system. As long as you are imposing these boundary conditions on the horizon, you will be computing retarded Green's functions. So imposing these boundary conditions, the infalling boundary conditions, or irregular boundary conditions on the horizon, will actually fix these constants of integration, okay? So you can basically, what I'm saying is that you can, yes, okay, you can fix the sources. You can put whatever you like in these other constants of integration, but in general, you will get something singular in the bulk. So if you want to get something regular in the bulk, you have to basically fine-tune these constants of integration so that everything becomes nice and smooth in the horizon. As long as you get something nice and smooth or something with infalling boundary conditions, if you are doing a real-time problem, then that will give you this unique, well, or discrete set of solutions for these other constants of integration, okay? Does that explain how you fix these constants? Is there any questions? Yes. Oh, yes. That I can choose to be whatever I like.
Okay.
But having regular boundary conditions in the bulk or infalling boundary conditions will fix me a unique value for this secondary constants of integration. Okay? More questions? Assuming that there is a horizon. Well, I'm also calling horizon, even if it's some singularity, but you can still have a sense of ingoing boundary conditions at the singularity. Yes. Of course, yes, you would need the full solution. Yes, this is where things become hard. You actually have to solve these equations of motion everywhere in the bulk, making sure that everything is nice and regular. Yes. Okay, now, I don't want to go through okay, so, right. All right, I think I should probably stop now, and then next time I will tell you how you read off the currents from these constants of integration. But what I want to make sure now is that we have established what it takes to fix these other constants. Okay? Good. Thank you.